All right, today we're going on a guided tour of one of the most powerful and, weirdly, most predictable forces on our entire planet, the tides.
So let's just start with a question to get a sense of the scale here. Think about this. What single force is strong enough to lift trillions of tons of water, to literally raise the level of the entire ocean, not just once, but twice, every single day?
Well, the answer isn't something here on Earth. It's actually a massive cosmic tug-of-war that's playing out in space between our planet and its neighbors. Okay, let's get into it.
So, our first stop is looking at the key players in this massive gravitational game. We've got the moon, the sun, and the very fabric of space they're constantly pulling on.
Okay, so the basic idea is this. Gravity from the moon and the sun is pulling on Earth's oceans. Now, this pull is strong enough to create two big bulges of water. One bulge forms on the side of the Earth that's directly facing the moon, but here's the part that really messes with your head. Another bulge forms on the exact opposite side of the planet. We'll get to why in a sec, but as the Earth spins, we pass through both of these high spots each day, and that gives us our two high tides.
Now, that brings up a pretty logical question, right? You've got two different things pulling on us. On one side, you have the moon. It's pretty tiny, but it's our cosmic next-door neighbor. On the other side, you have the sun, which is just unbelievably massive. Like 27 million times more massive than the moon, but it's also about 200 times farther away. So which one wins the tug of war?
The answer is kind of surprising. Proximity totally beats power. The moon's tidal force is more than double the sun's. And here's why. Because the moon is so close, the side of the Earth facing it gets a much stronger gravitational pull than the side facing away from it. It's that difference in the pull from one side of the planet to the other that really creates the tides. And in that contest, the moon wins, hands down.
So we've got these forces pulling on the ocean. But here's a huge misconception. The tide isn't really about water being lifted up. That vertical pull is actually super weak. The real work is done by horizontal forces, what we call tractive forces. Think about it. It's a lot easier to slide a heavy bucket of water across the floor than it is to lift it straight up, right? These tractive forces are what actually slide the ocean water into those high tide bulges.
So we've got these cosmic forces sliding the oceans around into two big bulges. But what does that actually look like on a beach in, say, California or a port in England? In this next section, we're going to see how that simple idea of two bulges turns into the complex but super predictable rhythms of the tide.
You know, depending on where you are in the world, you're going to experience one of three basic tidal patterns. A lot of places, like the east coast of the US, have semi-diurnal tides. That's two high tides and two low tides, and they're all about the same height. Some spots, like parts of the Gulf of Mexico, get diurnal tides, just one high and one low each day. And then much of the west coast of the US has mixed tides, where the two high tides every day are at totally different heights.
But these daily rhythms are just one piece of the puzzle. They layer on top of each other to create even bigger cycles that play out over a whole month. And these cycles affect how high the high tides get and how low the low tides go.
And that brings us to the famous spring-neap cycle. So twice a month, when you have a new moon or a full moon, the sun, the Earth, and the moon are all lined up. Their gravitational forces basically team up, and that creates spring tides, which, just to be confusing, have nothing to do with the season. These are your most extreme tides, the highest highs and the lowest lows. But when the moon is in its first or third quarter, it makes a right angle with the sun and Earth. Their gravitational pulls actually work against each other, which leads to neap tides, and those are way more moderate.
Now, if the Earth were just a perfectly smooth sphere completely covered in water, that would pretty much be the end of the story. But of course, it's not, and this is where things get really, really interesting.
Here's the crucial thing to remember. Those two big tidal bulges can't just sweep cleanly across the planet. They keep running into continents. These giant landmasses act like roadblocks, breaking up the simple global tide into this incredibly complex system of waves that get trapped inside ocean basins, just sloshing back and forth.
And this slide shows you the incredible result of all that interference. So on the left, you see the semi-diurnal or twice-a-day tide. See all that red and yellow in the Atlantic? That basin shape is just perfect for that rhythm. Now, look at the map on the right, which shows the once-a-day diurnal tide. The Atlantic is almost totally dead, but the Pacific just lights right up. The unique shape of each ocean basin really determines which tidal rhythm it prefers, and that creates these totally distinct global patterns.
And if you look really close at those maps from the last slide, you'll notice these spots where all the lines seem to come together. These are called amphidromic points, and they're one of the weirdest things about tides. Imagine you're swirling water around in a big bowl. The water on the edges goes way up and down, but right in the very center, the water level barely moves at all. That calm spot in the middle, that's an amphidromic point. The entire tidal wave for that whole basin literally pivots around that one spot.
So this whole sloshing effect, combined with the local geography, can lead to some truly mind-blowing extremes. Let's zoom in on the most famous example on the whole planet.
The Bay of Fundy, right between Nova Scotia and New Brunswick in Canada, is the undisputed world champion of tides. The difference between high and low tide can be over 50 feet. That is taller than a 4-story building. So, why here? What makes this one bay so incredibly special?
The secret isn't just about the shape of the bay. It's about a physics principle called resonance. See, any body of water, whether it's the water in your bathtub or an entire ocean basin, has a natural sloshing frequency. If you start pushing it at exactly that frequency, the waves just get bigger and bigger and bigger. That's resonance.
And this is just the perfect analogy. It's exactly like pushing a kid on a swing. If your timing is just right, they go higher and higher with every single push. Well, the shape and length of the Bay of Fundy mean its natural sloshing time is almost perfectly in sync with the 12.5-hour rhythm of the tide coming in from the Atlantic. So every incoming tide is like another perfectly timed push on that swing, sending the water higher and higher.
This diagram basically shows the secret recipe for that perfect tidal push. It turns out that a bay shaped just like this, one that's exactly a quarter of a tidal wavelength long, is a perfect energy trap. The incoming tide wave sloshes in, it hits the back wall and reflects back out, perfectly amplifying the next incoming wave. And this is why, as you can see, the tide is always highest right at the head of the bay. And guess what? The Bay of Fundy is almost this exact, perfect length.
So tides are obviously a fascinating physical phenomenon. But why does understanding all this really matter? Well, in our final section, we're going to see that these rhythms are woven into the fabric of our world in some really surprising ways.
I mean, that constant, predictable movement of water is an incredible force. Engineers are starting to harness it with underwater turbines to generate clean, renewable energy. The rhythm of the tides creates these unique ecosystems, like the huge mudflats that are vital refueling stops for millions of birds. But maybe the most surprising impact is in the law. Take a look at this diagram of a shoreline. You see that line labeled mean high water line? That's not just some abstract measurement for sailors. In a lot of places, that line, the average height of the high tide, is the actual legal boundary between public land and private property. So the next time you're at the beach, just remember that an invisible line drawn by the cosmos is what determines who owns the ground you're standing on. Pretty wild, right? And that brings us to a final thought. For thousands of years, we've lived by these ancient, predictable rhythms. But now, with sea levels rising, those legal lines are shifting, those ecosystems are under threat, and the very shape of our coastlines is changing. The cosmic tug of war is still going on, but the battlefield here on Earth is being redrawn right before our eyes.